Welcome! We are treating physics theory questions today. Question 1. Explain why mercury does not weight glass while water does. Answer. Mercury does not weight glass because force of cohesion/attraction of mercury molecules is greater than force of adhesion/attraction between glass and mercury molecules. Water weighs glass because force of adhesion/attraction between glass and water molecules is greater than force of cohesion/attraction of water molecules. Question 2. Explain what is meant by cations. Question 2. Explain what is meant by cations. Answer. Cations are positive ions that are attracted to the cathode during electrolysis. Draw and label an electrolytic cell. You can see the diagram on your screen. Correct diagram/sketch labeling cathode, anode, and electrolyte. Question 3. Question 3. State 3 methods of polarizing an unpolarized light. Answer. Polarization use of a polarized filter. The most common method of polarization involves the use of a polarized filter. Polarized filters are made of a special material that is capable of blocking one of the two planes of vibration of an electromagnetic wave. Remember, the notion of two planes or directions of vibration is merely a simplification that helps us to visualize the wave-like nature of the electromagnetic wave. In this sense, a polaroid serves as a device that filters out one half of the vibrations upon transmission of the light through the filter. When unpolarized light is transmitted through a polaroid filter, it emerges with one half the intensity with vibrations in a single plane. It emerges as polarized light. You can see the diagram. A polaroid filter is able to polarize light because of the chemical composition of the filter material. The filter can be thought of as having long chain molecules that are aligned within the filter in the same direction. During the fabrication of the filter, the long chain molecules are stretched across the filter so that each molecule is, as much as possible, aligned in, say, the vertical direction. As unpolarized light strikes the filter, the portion of the waves vibrating in the vertical direction are absorbed by the filter. The general rule is that the electromagnetic vibrations that are in a direction parallel to the alignment of the molecules are absorbed. The alignment of these molecules gives the filter a polarization axis. This polarization axis extends across the length of the filter and only allows vibrations of the electromagnetic waves that are parallel to the axis to pass through. Any vibrations that are perpendicular to the polarization axis are blocked by the filter. Thus, a polaroid filter with its long chain molecules aligned horizontally will have a polarization axis aligned vertically. Such a filter will block all horizontal vibrations and allow the vertical vibration to be transmitted. See diagram above. On the other hand, a polaroid filter with its long chain molecules aligned vertically will have a polarization axis aligned horizontally. This filter will block all vertical vibrations and allow the horizontal vibrations to be transmitted. The diagram below shows relationship between long chain molecule orientation and the orientation of the polarization axis. Polarization of light by use of a polaroid filter is often demonstrated in a physics class through a variety of demonstrations. Filters are used to look through and view objects. The filter does not distort the shape or dimensions of the object. It merely serves to produce a dimmer image of the object since one half of the light is blocked as it passes through the filter. A pair of filters is often placed back to back in order to view objects looking through two filters. By slowly rotating the second filter, an orientation can be found in which all the light from an object is blocked and the object can no longer be seen when viewed through two filters. What happened? In this demonstration, the light was polarized upon passage through the first filter, perhaps only vertical vibrations were able to pass through. These vertical vibrations were then blocked by the second filter since its polarization filter is aligned in a horizontal direction. While you are unable to see the axis on the filter, you will know when the axes are aligned perpendicular to each other because with this orientation, all light is blocked. So, by use of two filters, one can completely block all of the light that is incident upon the set. This will only occur if the polarization axes are rotated such that they are perpendicular to each other. These are diagrams showing teachers seeing through two Polaroids. A picket fence can act as a polarizer by transforming an unpolarized wave in a rope into a wave that vibrates in a single plane. The spaces between the pickets of the fence will allow vibrations that are parallel to the spacings to pass through while blocking any vibrations that are perpendicular to the spacings. Obviously, a vertical vibration will not have the room to make it through a horizontal spacing. If two picket fences are oriented such that the pickets are both aligned vertically, then vertical vibrations will pass through both fences. On the other hand, if the pickets of the second fence are aligned horizontally, then the vertical vibrations that pass through the first fence will be blocked by the second fence. This is depicted in the diagram below. The picket fence analogy. In the same manner, two Polaroid filters oriented with their polarization axis perpendicular to each other will block all the light. Now that's a pretty cool observation that could never be explained by a particle view of light. Polarization by reflection. Unpolarized light can also undergo polarization by reflection of non-metallic surfaces. The extent to which polarization occurs is dependent upon the angle at which the light approaches the surface and upon the material that the surface is made of. Metallic surfaces reflect light with a variety of vibrational directions. Such reflected light is unpolarized. However, non-metallic surfaces such as asphalt roadways, snowfields, and water reflect light such that there is a large concentration of vibrations in a plane parallel to the reflecting surface. A person viewing objects by means of light reflected off of non-metallic surfaces will often perceive a glare if the extent of polarization is large. Fishermen are familiar with this glare since it prevents them from seeing fish that lie below the water. Light reflected off a lake is partially polarized in a direction parallel to the water surface. Fishermen know that the use of glare-reducing sunglasses with the proper polarization axis allows for the blocking of this partially polarized light. By blocking the plain polarized light, the glare is reduced and the fishermen can more easily see fish located under the water. You can see the diagram below. Polarization by refraction. Polarization can also occur by the refraction of light. Refraction occurs when a beam of light passes from one material into another material. At the surface of the two materials, the part of the beam changes its direction. The refracted beam acquires some degree of polarization. Most often, the polarization occurs in a plane perpendicular to the surface. The polarization of refracted light is often demonstrated in a physics class using a unique crystal that serves as a double refracting crystal. Iceland spar, a rather rare form of the mineral calcite, refracts incident light into two different parts. The light is split into two beams upon entering the crystal. Subsequently, if an object is viewed by looking through an Iceland spar crystal, two images will be seen. The two images are the result of the double refraction of light. Both refracted light beams are polarized, one in a direction parallel to the surface and the other in a direction perpendicular to the surface. Since these two refracted rays are polarized with a perpendicular orientation, a polarizing filter can be used to completely block one of the images. If the polarization axis of the filter is aligned perpendicular to the plane of polarized light, the light is completely blocked by the filter. Meanwhile, the second image is as bright as can be. And if the filter is then turned 90 degrees in either direction, the second image appears and the first image disappears. Now that's pretty neat observation that could never be observed if light did not exhibit any wave-like behavior. The diagram is displayed on the screen.